All right, so let's examine this new discovery here. So we have this fundamental theorem of calculus, right? It's actually part 2 of the fundamental theorem of calculus, and sometimes you'll hear people call it FTC, or sometimes FTC2 part 2. Anyway, so let's examine the usefulness of this. So if we didn't have the fundamental theorem of calculus, once again, we would have to draw this picture out, right? And somehow find the area underneath, or not necessarily draw the picture out, but this is one way to do it. This would be a parabola at crosses at -4, symmetrical about the y-axis, etc. It would cross here at 2 and -2. Okay, and somehow we'd have to find we want the integral from -2 to 2, so we'd want this area right here, right? We don't have a geometry formula for it. So what we'd have to do is we'd have to plug this into the definition, right? And we'd have to do the Riemann sum and break it up and FOIL, and it'd be a process. So now what we can do is we can say, all right, well, let's start with just taking the antiderivative of this, right? So let's take the antiderivative. So that this would be, if I was looking for capital F of t, and I'm using t because that's the given variable here, the designated variable. And so the antiderivative of this would be t cubed over 3, right, minus 4 times t, right? And then what do we always have to remember to do with indefinite integrals or antiderivatives? Remember, we always add the constant, right? But I'm putting that in a different color here because you'll see in a minute that there's something that happens with the constant. Let me put it that way without trying to spoil anything. So we'll keep it at that for now. So remember that our theorem says, fundamental theorem of calculus says that if I plug in b to the antiderivative and then plug in a to the antiderivative and subtract those values, that will give me the area under the curve. Okay, and so anyway, that's what we'll do. So what I'm going to do is I'm going to do f of 2, right, that's b, minus f of -2, which is a, right? And so f of 2, if I plug 2 into this function here, then I'm going to get 2 cubed over 3 minus 4 times 2, right? Plus that constant, and I'm going to leave that constant in a different color there, okay? So that's f of b, right? Now I'm going to subtract f of a, right? F of -2. So I'm going to do, it's going to look exactly like this, except for I'm just going to have a -2 in there, right? -2 cubed over 3 minus 4 times -2, and then plus a constant. All right, and we'll see what happens with that constant here in a second. Let me just give us a little more space here. So now it's just a matter of evaluating, right? So you can see how this is a lot more streamlined than using the definition of the definite integral, right? And it's a lot more universal than having to use a geometry formula, which wouldn't apply to this parabolic situation, right? We don't have a formula for a parabola, top there, bottom, with anyway, we don't have that formula. So let's evaluate this and see what we get. So 2 cubed over 3, that's going to be 8/3. 4 times 2 is 8, so it'll be minus 8. And then we'll have plus a constant, right? And then here on this side, I'm going to have to distribute this negative to everything, and I'll do that while I'm evaluating. So I'm going to distribute the negative, and I'll do that while I'm evaluating. So I'm going to have -2 cubed is -8, right? But I have a -8, so that's going to turn into +8 over 3. And then here I have -4 times -2, which is +8, but then I'm going to apply that negative to it, so it's actually be -8, right? And then I have negative applying to this positive c, so that's actually going to be -c, right? And so this is why I wanted to show you the constants in here, is because what happens always, if you're subtracting f of b minus f of a, you're always going to have a situation where those constants cancel out, right? Because here your constant will be plus c, and then when you subtract, you'll have minus c, and so they will always cancel out. So when you're dealing with the definite integral, you can ignore the constant. Okay, you can definitely write it in, like there's nothing wrong with that, but you can also ignore it because you know that it's going to cancel out. So you can just focus on the other values, and you don't have to focus on the constant when you're dealing with definite integrals, definite integration. Okay, definitely if it's indefinite integration, or if I'm asking for the antiderivative only, then definitely include the constant. But if you're dealing with the definite integral here, where you have an a and a b, then you can ignore the constant. All right. So now let's combine these terms here. So like terms. So we have 8 thirds plus 8 thirds is 16 thirds, and negative 8 minus 8 is negative 16. So now what I want to do is I want to get a common denominator. And you can do this a lot of different ways. You don't have to show all this work as far as like the operations here. You can do mental math. You can do it in your calculator, that sort of thing. I trust your abilities in that regard. So I'm converting this to 16 over 1, and then I'm just to get converted to a fraction, and then I'm multiplying by 3 to get a common denominator, and so that's how I get negative 48 thirds, as you know. And then 16 minus 48 is negative 32 thirds. All right, and that makes sense that we have a negative area, right? Because this area is all below the curve, and so yeah, that's our answer. So definitely some computation, some evaluation there, a little bit of antiderivative work, right? So we're bringing that back into play now, and but yeah, a lot more conventional way to find a definite integral. This is pretty much the standard way that we'll find the definite integral. So we're not going to use area formulas. We're not going to have to draw the curve. We're not going to use the definition of the definite integral. Generally, if you have a choice and it just says evaluate, this is the way that you're going to do it. Okay.